Hello physics students. Welcome to this video where we're going to begin studying the next topic in physics. But before we jump into that, I first want to take a step back and look at the big picture again of what it is we're doing in studying physics. Before we even began talking about forces, I said that the goal of physics was to understand the universe for all space and all time. So that means that you're thinking about enormous large things, like when you're looking across the universe at a tiny blinking light in the night sky, which may be an entire galaxy of billions of stars. So physicists want to know all that's in between, what's happening on that, inside that galaxy, within all the stars. So those are all questions and things that physicists want to investigate. And down to a small level, like within a single atom inside you, there's protons, neutrons, electrons, even smaller than that. Physicists want to study that. So we began with that in mind, that we were thinking about, our goal was to understand all of that. And then we said, or I said, that the way that everything evolves is with force. Pushes or pulls that can come from living things or inanimate objects. Everything creates force, and that forces can push things to make things move, or forces can act on something to keep something at rest. And then we delved into forces mathematically. So what that meant is that we were able to come out and calculate things like the net force, down to like a millionth or even a billionth of a Newton. We could get very precise with two forces, for example, perpendicular to each other, and use the Pythagorean theorem and come out with the net force and the angle or the direction. And this applied not just to the blocks that we were studying in physics class, but also maybe even to two black holes way out there in outer space orbiting each other. And maybe a rock is flying between and it's going to get pulled into one black hole or another. And then there's going to be net force, two forces between the two black holes and a net force on that rock. The same procedures that we used in the last topic, you can use in deep outer space to figure out the net force. So we have a very mathematical, complete, deep understanding of forces. But think about it, we're still very incomplete in our knowledge. We can figure out the net force on that rock, like I said, down to the billionth of a Newton maybe. And then it moves as a result of that net force, that rock. But then when it moves, we're just sort of describing it. We might say it shot like a bullet toward one black hole. So we're using words, imprecise ways to describe the results of the force. So what good is that precision with the forces if we can't then describe the resulting motion as precisely with formulas and numbers? Not much good at all. So that's the purpose of this next topic, is now to look at the motion that results because of the forces and come up with a mathematical way to describe those resulting motions, formulas, numbers, okay, down to maybe the billionth or something like that. So that's the second topic, called kinematics, okay? So this is the unit plan. You hopefully printed it out already. And if you look at the subtitle, kinematics is a mere description of motion. We're not saying exactly why the motion occurs, but we want to catalog it with formulas and numbers as precisely as we cataloged the forces that are causing that motion. So that's it in this topic, just mathematical description of motion. So today we're going to begin with a bunch of definitions of different ways to mathematically describe motion. I'll step aside, give you a chance to copy this first portion of notes down before I explain. So go ahead and copy. Okay, so the first thing, these are general terms that are not necessarily specific to kinematics. They apply to all science. The idea of a scalar and a vector. So a scalar has magnitude only, and magnitude is a fancy word for size. The Regents curriculum likes to use that word instead of size. So when you say, see, what's the magnitude of the net force? They're looking for the numerical size of it. So scalars have magnitude, whereas vectors have magnitude and direction. So they're more specific. An example of a scalar I mentioned in topic 1 with force would be like the temperature of the room. If it's 70 degrees in here, it's still 70 degrees. I didn't change the temperature by turning myself or the thermometer, so temperature doesn't have a direction. But force does, right? If I push something, right, up with 1 Newton, I'm holding it up. If I push it down with 1 Newton, I'm throwing it into the floor and it smashes. So that is definitely direction matters with force. So it is called a vector. All right, so knowing those two ideas, we're going to move into the first of the 3 ideas that we're going to study today, okay, that are the foundation of all of kinematics, by the way. Distance versus displacement is all together as one kind of idea of more or less where something is in space. So distance is the scalar, you see the color coordination, and displacement is the vector. Now, rather than define this with sentences, I like to define with examples because they kind of more quickly give you an idea of what each is. So let's suppose I'm going to walk 5 meters to the right, which on a map would be in the east direction. I turn around and I go 3 meters in the backwards direction towards the west. So the distance I walked is just the total of 5 plus 3 or 8 meters, right? Common sense. Or you could say I went out for a run, I ran 5 miles and then I turned around, ran 3, you ran 8 miles, right? So it doesn't matter that you turned around for distance. But with displacement, your displacement is like the net motion from where you started to where you ended. That's all that matters for displacement. So if you look, here's our starting point, here's our ending point. We ended up with a net motion of 2 meters towards the east. Because it's a vector, we need direction also. So displacement's like the net motion. It's possible to go on a journey and have 0 displacement. You go outside your house, open the door, and you jog 3 miles. You turn around and you jog 3 miles home. Maybe you're getting ready for track or something. So you ran 6 miles distance, 0 miles displacement because you began and ended at the same point. Okay? Another example, walk 2 meters, 4 meters, 2 meters. Your distance is 8, just adding up all those. But your displacement is your net motion from the starting point, right there, to your ending point right there. Along a straight line, you moved 4 meters to the east. That's the displacement. By the way, this little symbol, I forgot to mention it. It's like an arrow. You could write displacement like this. Oh. You could write displacement like this and draw a full arrow over it. But usually they just do a half arrow so it's a little quicker. But basically it's just indicating like an arrow. So the symbol is a D with that little arrow over it for displacement. Okay? And also, as you can see, it's measured in meters. So that's one idea. And if we describe the displacement of something through all time, that's enough to mathematically state the motion of something. If I say that I'm going to walk along a line and my my x coordinate, which will be kind of like my displacement, will be 2t, 2 times time. That function tells me that at 1 second I'm 2 meters away, then 4 meters, 6 meters. It tells my motion mathematically. So we'll get more in detail with that, but it's enough if you tell an object's displacement, that's enough to tell its motion. But there's another way we could describe motion. That's with how fast it's going, which brings me to the next idea or two different specific, but all of these deal with how fast something is going. Speed versus velocity. By the way, this is a symbol V, and instead of writing V like this, you can, by the way, and you won't lose points. Usually physicists write a cursive V because a capital V is reserved for something else that we're going to be studying later in the year. And sometimes you get confused between those two. So you don't get confused with voltage and velocity or speed. You do the curly V for speed. So speed is the scalar and velocity is the vector. So I'll pause, allow you to copy this down before I explain in more detail. Okay, so first of all, the formula for both of these, okay. There's no vector symbol over the speed. I apologize for that, but you're going to have to erase that in your notes. Okay, so the same formula, whether you're calculating speed or velocity, you're basically taking distance over time for speed or displacement over time for velocity. But speed is in meters per second in R units, in physics units. In everyday life, of course, you know speed, you usually use miles per hour, okay? But basically what speed is it's how many meters you move in 1 second. So if I march like this, and I'm marching at 1 second intervals, I'm moving 0 meters every second, every time I step. If I move 0.1 meters per second, that means 10 centimeters, so I'll move 0.1 meters per second. And you see that's a slow velocity, okay? How about if I move 1 meter per second, right? And now you see I went across the screen pretty quickly, 1 meter per second. Humans can run, the fastest human, about 10 meters per second. So that's about as fast as a human can run. By the way, a rough estimate, if you wanted to compare meters per second to miles per hour, then basically you about double the meters per second, and that's roughly the miles per hour. So 10 meters per second, a person running is about 20 miles per hour. You could look up the more precise conversion, but just so it gives you an idea in your head. This table demonstrates kind of more the concept of speed. So this object right here is distance 1. Both objects started at, say, distance or displacement 0. So they're starting at some starting point together. One object every second is advancing 0, 2, 4, 6, 8. So that's like the total distance the object traveled. And what you could see is that every second, this object is going 2 more meters. So it goes 2 meters per second. This object goes from 0 to 5 to 10 to... So this object, you see, every second, it's increasing its displacement by 5 meters. So it goes 5 meters per second. And you see that something that goes 5 instead of 2 ends up going further, which makes sense, right? You go faster in your car over a certain amount of time. You're going to go farther than someone else who went slower, okay? So it's kind of very logical, okay, to describe motion in terms of speeds or velocities. All right, what I want to do is do an example because I always like to show the kinds of things that I believe are trick questions that the Regents likes to throw on the Regents test. So pretty easy if they give you 2 of these, you have to solve for the third. You plug it in, you solve for maybe speed, they tell you 2 meters a second, how long does it take 20 meters, and you solve for t, right? So those kinds of problems probably you'd be okay with. But something like this trips up a lot of people. Okay, so let's suppose, you know what, instead of words in this, for the sake of speeding things up, let's suppose that I just give you a diagram of, so let's see, something moves this way. Let's say it goes 20 meters in 4 seconds. Okay, let me just see if that shows up all right, the green. Okay, I think so, yeah. So 20 meters in 4 seconds. And then it turns around and goes 4 meters. Oh, maybe I'll use blue. In 2 seconds, backwards. And the question is, determine average speed and average velocity. Okay? So, a lot of students see the word average and they would tend to do something like this. They would say, and don't write this down because it's incorrect. So the speed here is 20 over 4. I'll leave the units off because I'm just kind of scratching here to show. And that's 5. The object went 5 meters a second in the forward direction. And then this, it went 4 meters over 2 seconds, which is 2. Average those up, and again, you're not jotting this down because it's not correct. You say, oh, I know how to do an average. I'll add them up and divide by 2. So 7 over 2 is 3.5. Not correct. So I'll put 3.5 here as what we got for the average of those two numbers. So, and again, that's what why the Regents puts a question like this on, in my opinion, why they do that. To get you to do that and get the question wrong. They like people getting questions wrong. The way to get average speed is to simply use total distance over total time. So this is part A, average speed. And the total distance, this object went 20 meters and 4 meters. So we do 20 meters and the 4 meters, total distance over the total time. And the time was 4 seconds and 2 seconds. And when you divide that out, 24 divided by 6 gives you 4 meters per second. Not 3.5. And you might be asking, why doesn't that work, taking the average this way? The reason why is because the object spent more time at 5 than it did. It spent 4 seconds moving 5 and only 2 seconds moving 2. So that extra time traveling 5 shifts the average closer to 5. The analogy would be like this. You take physics tests all year and you're great at physics. 100, 100, 100, 100, 100 all year. And then the last test you say, yeah, I've been doing great in physics. I'm going to the beach. I'm not going to take the last test. So out of 9 100s, you got 1 0. And I say, I know how to take an average. I'm going to do 100 plus 0 divided by 2, 50. That student failed. No, that student didn't fail. They had 9 100s, more 100s, so the average should be closer to 100. I would do 100 plus 100, 100, 9 times plus 0 divided by 10, and I'd get a 90. So the 90 would be closer to 100 because there were more of them. Same thing here. More time at 5 means the average should be shifted closer to 5. The only way is total distance over total time. Now, the velocity, you would do a similar calculation, average velocity, and I'll put a vector over the v, would be displacement over time. Total displacement. So what I have is in the forward direction, now with displacement, direction matters, it's a vector. So I'm going to call this positive 20. And this is backwards. So I've got to indicate backwards. Maybe I'll put -4. And then the time would be the 4 seconds and the 2 seconds again. But we don't subtract time, right? It doesn't make sense to subtract time. Time just keeps running forward, doesn't run backwards. Maybe sometime it'd be nice to have it run backwards, but... So now what we get is 16 divided by 6 seconds. So that would give us 2.7 meters per second. And maybe we'll put a positive because it's in the forward direction. So the average velocity is that. So that's the one example I wanted to do with speed and velocity calculations, because like I said, I believe it's a trick question that comes up often. Okay, so we had distance, displacement, speed, velocity. I'm going to erase to make a little room for our third and final idea. Okay, so if you haven't already done so, I'll pause the video to give you a chance to jot this down. Okay, third idea. We could describe an object's displacement. That's good enough to describe its motion mathematically. We could describe its velocity or its speedometer reading at all times. That's enough to describe the motion mathematically, numerically. Or we could describe the object's acceleration. So the symbol for acceleration is A, lowercase a. By the way, it's always a vector. I could put this, but you don't need to, because acceleration is always considered a vector. So you've heard the term. Let's define it mathematically now. A is this. Change, that's what that triangle means, delta, right? Change in velocity over time. Okay? So any change in velocity, you are accelerating. So before I put the units over here of what it's measured in, I just want to look again, before jumping into the specifics, exactly what acceleration is. An obvious thing that people tend to always get right is that acceleration is speeding up. In fact, some of you have been driving, maybe you have your licenses already. The gas pedal of a car is actually called an accelerator. So you step on the accelerator and you start speeding up. Faster, faster, faster. Okay? But any change in velocity, and increasing is changing the velocity, but so is decreasing. So slowing down is also acceleration. If you were strictly thinking in terms of physics, the brake pedal is also an accelerator. Some people say, wasn't that a decelerator? You could use the word deceleration, and that's perfectly fine even in physics class. But you must know that slowing down is acceleration also, not just speeding up. And another thing, velocity can increase, decrease, but it also has direction. So changing the direction is also acceleration. In other words, turning. Okay? All three of these acceleration, you have to know that in physics. Okay? How is turning acceleration? Well, let me just talk a little bit more about that. So you're going in your car, you're going down the road, straight line, straight road. Your speedometer reading is fixed at 60 miles an hour, 60 miles an hour, 60 miles. No change in velocity per time. Zero acceleration means you're going steady. Doesn't mean you're stopped. It just means you're going steady. Okay? And then you're going down the road. So I draw the velocity like this because you're heading east. The road curves, and I'll put 60 for 60 miles an hour. And then later, you're going 60 this way. That's not the same arrow. It changed. So that change of an arrow, acceleration, because the velocity changed. So you're going around a corner, 60 miles an hour, 60 miles an hour, 60 miles an hour, 60 miles an hour. The entire time your speedometer never changed. But as you were turning, you were accelerating. Okay, so that a lot of people don't get. But you're going to get it, right? Because now you know. Next time you're maybe in driver's ed and the instructor tells you, okay, let's go, press down the accelerator, honk the horn, right? The steering wheel is an accelerator too, as is the brake pedal, as is the gas pedal. All the controls in a car are accelerators, okay? They cause acceleration. The units, okay? We have, and don't write this down because I'm going to change it, meters per second in the top and seconds for time. Some people say that's meters. It's not. You're dividing by seconds twice. So what that actually means is the units for acceleration are meters per second squared. Okay, so that's the unit. Now, acceleration isn't just speeding up, slowing down, turning. It's how fast those are happening. We haven't talked about the time part. I could be in a 30-year-old clunker, okay, barely runs, and I go 0 to 60. I press the gas pedal down, the car's shuddering, smoke coming out the back, right? And a long time later, I'm up to 60. Someone else in a brand new Lamborghini floors the gas pedal, they're going 60 in less than a fraction of the time, or in a small amount of time. We don't have the same acceleration, even though we both went 0 to 60. The thing that did it in the least amount of time had the most acceleration. So, let me look at some examples to show you. Okay. So, if you already haven't written that down yet, I'll pause the video to give you a chance to jot that down. Okay, let's continue on. So, let's suppose, I don't have a short ruler. I guess I could do it with this. This is my old school speedometer, right? Speedometers in the old days, they had like a needle like this. So let's suppose a car has an acceleration of 1 meter per second every second. So I hit the gas pedal and my speed goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going 10 meters per second, or let's say 10 miles per hour, with an acceleration of 1. So that's what acceleration, every second the speedometer went up by 1. Someone else has an acceleration in a car that's 10 instead of 1. So instead of going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, in 10 seconds, they go 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. They're going 100 in the same amount of time because every second they went up by 10, not by 1, more acceleration. So that's kind of what acceleration is. It's the increment that you gain or lose every second. Said it a better, more general way, it's what you're adding to your speedometer reading every single second, provided you're not turning. So a lot of people then will say, okay, and don't write this down. One person speedometer reading went 0, 2, 4, 6, and another went 0, 10, 20, 30, right? So this one had the greater acceleration every second, adding 10. So then they say, well, positive acceleration means you're speeding up because your speedometer is going up. And then if after this I start going 20, 10, 0, notice I'm adding -10 here. So they say, well, positive acceleration, speeding up. Negative acceleration, you're slowing down. And it turns out that's not always true. So this is the final thing that I want to show, an example. Okay, so let's create a table with time over here. And over here, speed, or velocity, I should say. All right, so let's suppose I've got a time that begins at 0, 1, 2, 3, 4, 5. That should do, okay, 6 seconds. And in the beginning, I'm moving forward at 6 meters per second in my car. And then I'm going 4. Oh, I don't need the meters per second, right? I got it in the top there. 4, 2, and then 0. What could cause this? Possibly my brake pedal. Or another possibility is I'm going up a hill at 6 meters per second and then I run out of gas. And the car is going to slow down because it's, the hill wants to go this way. So it coasts and it's slowing down because of the gravity on the hill pulling it the opposite way. We'll talk more about that in the next topic. So that's possibility. Now, what's the acceleration as I'm slowing down? Well, what am I adding to my speedometer every second? -2, -2, and -2. So my acceleration here is -2 meters per second every single second. You write that like that. So negative acceleration is slowing down, right? Well, let's suppose I reach the top of the hill and I don't put the brake on and then I start rolling down the hill backwards. What happens to my velocity? Well, backwards now is negative velocity and I have -2. But I'm rolling down the hill, picking up speed, faster, 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 because I'm not putting the brakes on. Now I'm going faster and faster down the hill. And I'm going faster in the backwards direction. And now let's ask ourselves, what do we add to our speedometer every single second, which is what the acceleration is? -2. What do I add to -2 to get to -4? I add another -2. How do I get to -6 from -4? I add another -2. So in this phase of the motion, my acceleration is still negative. But notice I'm going faster and faster and faster in the backwards direction. So negative acceleration, at one point I'm slowing down, and then the same negative acceleration I'm speeding up. So how do we tell if an object is speeding up or slowing down from its acceleration? Well, all right. Maybe I'll pause here and let you get a chance to copy this back down in your notebook. And then so if acceleration, I'll just put ACC, and velocity have the same sign. And what I mean is plus, plus, or negative, negative. The object speeds up. If the acceleration then the object slows down. I'll pause the video, give you a chance to jot this down. So, positive acceleration, positive velocity speeds up. Negative velocity, negative acceleration also speeds up. You're gaining what you already have. You're gaining what you already have, so you're getting more of that velocity, you're speeding up. But if they have opposite signs, like the velocity is positive and the acceleration is negative, or the velocity is negative and the acceleration is positive, you're adding the opposite of what you have, your number's getting smaller. You're adding the opposite of what you have, your number's getting smaller, you're slowing down. Okay? So that's it. 3 ideas to mathematically describe the motion of an object. Distance and displacement are 2 related ideas, fall under category 1, the meters. Speed, velocity, how fast something is going, the distance per time. And the acceleration, how rapidly you're speeding up, slowing down, or turning, or how rapidly your velocity is changing. State any one of those mathematically or numerically, and you've mathematically or numerically described the motion of something very precisely, okay? All right, I'll see you in the next physics video.